Okay, welcome back everyone to our second lecture of the day. Please, Bill, you have the floor.
Thanks very much, Gabriel. Told you yesterday that I have my own perspective on things, and I've spent the first 2 days basically trying to get you to buy in to the calculations that I want to do today and tomorrow. And so on Monday, I tried to convince you that there exist Q-polynomial association schemes that aren't P-polynomial. So cometric association schemes, and we spent our time on Monday on imprimitive schemes with small numbers of classes. So 4-class Q-bipartite Q-antipodal schemes are real mutually unbiased bases. 3-class Q-antipodal schemes are linked systems of symmetric designs. We didn't talk about linked systems of strong irregular designs. There's a beautiful example in my paper with Edwin Van Dam and Misha Muzicek that we saw in Higman's paper, where you have 150 vertices on each of the 3 antipodal fibers is induced a Hoffman-Singleton graph, and between any 2 of the fibers is a Higman-Sims graph. So there's beautiful, beautiful structure in some of these examples. We didn't have time to talk about Higman, but we mentioned that the shortest vectors of some of the lattices, some of the most famous lattices are Q-polynomial association schemes, and Akihiro Munemasa has a chapter in the Handbook of Combinatorial Designs where he talks about Q-polynomial schemes that come from lattices. And the second day said, well, are there any primitive examples? And we found that there are an infinite family of primitive examples found by Quintilla and Williford. There's an infinite family of new imprimitive examples with arbitrarily large class number found by Morehouse and Williford. But the smallest Q-polynomial example that I know of that's not P-polynomial is just the blocks of the small Witt design. So if you take the small Witt design, so it's a 4 design, so you have a bunch of 5 subsets of an 11 set with the property that every 4 set is in a unique one of them. And so the strength T is 4, it's a 4 design, and the number of block intersections S is equal to 3. And there's a standard theorem of Delsarte of T at least 2S minus 2, then inside the Johnson scheme, you induce a cometric or a Q-polynomial subscheme. And those Q-polynomial subschemes that come from type designs, you'll notice right here that the first entry in the Kreiner array is 10, and you probably can tell me why it's 10, because it inherits its eigenspaces from the Johnson scheme. That's exactly the dimension of the eigenspace of Johnson, right? Of Johnson 11.5. Right? So it's inheriting its eigenspaces from the ambient association scheme. Okay, so we talked yesterday about so many problems where you have a natural thing to talk about in distance regular graphs, and if you look at the dual question, many of these are unsolved. Some of them are conjectures, some of them are partially proved, and in particular, there are the 2 Suzuki theorems. One, when it's all put together, says that there are most 2 Q-polynomial orderings, and they're exactly the dual of the 2 P-polynomial orderings you would see for a distance regular graph other than a polygon. And the second one says that if a cometric association scheme other than a polygon is imprimitive, it's either Q-bipartite or Q-antipodal. And my goal today is to talk about those theorems. I'm going to repeat a couple of things, and you're tempted probably to skip over the introduction. I'm going to go very quickly through the definition of an association scheme from the adjacency matrix viewpoint. So instead of a collection of graphs partitioning X cross X into binary relation, we can think of a bunch of 0-1 matrices. It's equivalent to just thinking about the relations. We can think about their adjacency matrices. We have a collection of 0-1 matrices with rows and columns indexed by X. Their sum is the all-ones matrix. One of them is the identity matrix, and we always choose A0 to be the identity. And the vector space spanned by these is closed under matrix multiplication. Multiply AI and AJ. It's a linear combination of the AKs, and those are exactly the intersection numbers Pijk. So this algebra is the Bose-Mesner algebra, and because the AIs are representing disjoint relations, the adjacency matrices have the property that AI entry-wise AJ is 0 if I is not equal to J, and they're all sure idempotents. At the second basis, the basis of projections onto the maximal common eigenspaces, E0 up to ED, and E0 is a scalar multiple of the all-ones vector, or all-ones matrix. the projections sum up to the identity, which is the projection onto the entire space. They're symmetric matrices, and because the vector space is closed under entry-wise multiplication, the entry-wise product of EI and EJ is some linear combination of the EKs, and these non-negative real numbers are called the Klein parameters. And I'm particularly focused on those Klein parameters. Paul calls the eigenspaces EJV. That's a really nice combination. I call it VJ. Just translate between the two when I don't include both. I want to think about these matrices of parameters. So if you fix I, J, or K, let's fix I. If I look at the P, I, J, K, it's where K index is the row and J index is the column. It's called the ith intersection matrix. Really, the Klein matrix, L sub r star, has all of the Klein parameters QRST in row T, column S. And this is the matrix I'm going to spend a lot of time on today. So I want you to think about how that matrix is built. In particular, column S of LR star is the expansion of ER entry-wise ES in terms of the basis of primitive idempotents with the scalar that I'm going to ignore. Column S of LR star is exactly the same as column R of LS star. It's duplicated information. So you have to keep track of the fact that these things, whenever you have information about a column of LR star, that gives you information about some column of LS star. So Philippe Delsart realized that distance regular graphs are exactly the P-polynomial association schemes. I guess probably Biggs and some others knew that beforehand. The P-polynomial association scheme is one where you can order the relations A0 up to AD so that Pijk is 0 if any one of the parameters is bigger than the sum of the other two, and Pijk is non-zero if one of the parameters is exactly the sum of the other two. And the really beautiful thing was to just dualize this and trust that it's beautiful, and it really is a beautiful concept, to say an association scheme is cometric or Q-polynomial if you can order the eigenspaces so that Qijk is 0 whenever one of them is bigger than the sum of the other two, and it's non-zero. I'm going to use a black box for non-zero if one of them is exactly equal to the sum of the other two. So today, what I want to do is I want to give you most of the proof of this fundamental lemma that Paul uses, that everybody uses, from Cameron, Goethals, and Seidel. And I'm going to use scaffolds tomorrow to prove the Boxton lemma and the Dickie's lemma. I make up names for these things. I apologize. I have my own names for these things. The Boxton lemma and Dickie's lemma. And today we'll prove the Diamond's lemma. And these tools very, very quickly give us a theorem which implies both Suzuki's theorems, with limiting boundary cases being technical things that I'm going to ignore for now. Okay, so the weak versions of these theorems follow from that. So this is where we're going today. So you're just going to get sound bites of some of these things. So we're just going to see some of these things in just very, very simple form, and maybe that's all you have the patience for anyway. Okay, so Garth Dickie's lemma, which tomorrow you'll be able to do this. Garth Dickie's lemma says if you look at the Klein array, Bi star, Ci stars, so now L1 star is tridiagonal. I have a Q-polynomial ordering. L1 star is tridiagonal, and the Bi stars are the things just above the diagonal, Ci stars are just below the diagonal, and Ai star is on the diagonal. If any one of the Ai stars is 0, other than the last one, right? If Aj star is 0 for any j less than d, then A1 star is 0. Okay, so we're going to use that a lot, but I don't have a proof today. I really like to take entry-wise products of vectors. So Paul called this the function algebra last week, and so you're familiar with this if you've been here with us last week. So I want to control the entry-wise product of a vector in the ith eigenspace with a vector in the jth eigenspace. It seems hopeless because that's completely outside the control of the Bose-Mesner algebra, but at least I know that this is true if I have a vector u, which is the first column, or any column, let's say the first column of the projection matrix EI, and V is the first column of Vj, then I can just look at the first column of each side of this product, and I find out that the entry-wise product of those two vectors is orthogonal to the kth eigenspace if and only if Qijk is 0. So what if I took the first column of EI and the seventh column of EJ? Algebra doesn't tell us what we can do there. But it turns out that there's something very, very nice. So embedded in this beautiful paper of Cameron, Goethals, and Seidel is this very simple fact that is so useful. If U is a vector in the ith eigenspace and V is a vector in the jth eigenspace, and the prime parameter is 0, then U entry-wise V is orthogonal to the kth eigenspace. This is so fundamental. It's so simple, it's so fundamental, and it's so, there's so much we can do with it. Okay, so there's this technical lemma that is sort of a simplified version of this is in BCN, but I don't know if this is appearing anywhere other than my paper on symmetric designs. So EK times the diagonal matrix, EJ, the Frobenius norm squared of that is calculated exactly in terms of the inner product of this U transpose ELU for each eigenspace. So this is a really nice formula. And once you have that formula, now if I let U be this element of the ith eigenspace, and if V is in the jth eigenspace, then V is equal to EJ times V. And now I just take this equation and multiply both sides on the left by delta U, the diagonal matrix. That's the same thing as entry-wise product of U on the left, and multiply by EK. And it turns out that that must be 0 because the only thing that shows up here is L equal to I, because U is actually in the ith eigenspace. Okay, so this comes out very quickly. So we have this. One way to see this, so this shows up in so many different forms. I'm going to write down different versions of this simple fact. Okay, so if U is in the ith eigenspace and V is in the jth eigenspace, and the prime parameter is 0, then it's the entry-wise product is orthogonal to the kth eigenspace. You can also take all possible entry-wise products of things in the ith eigenspace and things in the jth eigenspace. We know that the columns of EI and columns of EJ, those sometimes end up non-orthogonal to the kth eigenspace because the prime parameter is non-zero. So it turns out that this collection of entry-wise products is orthogonal to VK if and only if Qijk is 0. Now this was in Paul's slides last week where Paul defined VI entry-wise VJ to be the linear span of these things, but I'm sort of interested in this manifold and the ideals of things that vanish. And so, I'd like to not take the linear span right now. In the Théorie theory, this is expressed exactly as EI, AJ star, EK is 0 if and only if Qijk is 0. Same fact. It's all the same. Okay. Another way is if I take the entry-wise product of a column of EI, a column of EI, and column B of EJ, and column C of EK, I take the entry-wise product and take the dot product of the all ones vector, that's 0 if and only if, for all A, B, and C, if and only if the prime parameter is 0. Okay, so that's equivalent. Build a tensor, right, with think of a three-dimensional box where there's one coordinate counting all the A's, another one counting all the B's, another one counting all the C's, right? And what you have is the third-order tensor, which vanishes if and only if the prime parameter is 0. So this is what we're going to do tomorrow. This is the basic starting points for tomorrow, is that this scaffold, this tensor is 0 if and only if prime parameter is 0. Now there's a rule for the Pijks, you're counting triangles. You want to check Pijk is 0 if and only if it's impossible to find a set of vertices A, B, and C such that A is I related to C and K related to B and C is J related to B. We saw in Akihira's talk this sort of change between the star and the triangle, many people, Hajime Tanaka knows a lot about these things, and he called them star triangle diagrams. I called them scaffolds. We'll talk about those tomorrow. So this fundamental lemma shows up as a building block in all of the scaffold computations tomorrow and Friday, based on this this interpretation. Here's something so trivial. I love this. It's so trivial. the inner product of U entrywise V, it's a real number, let's not take the Hermitian inner product. Inner product of U entrywise V with W is the same as the inner product of U with the entrywise product of V and W. Same thing as the inner product of U with the entry product. Right? You're just taking triple products and then summing them over all vertices, right? And you can also put all the U, V, and W on one side and take the inner product of the all-ones vector. That's what we did at the top of the previous slide. Right? That was just the triple product, entrywise product of the all-ones vector. Now, we know that we have Q-polynomial conditions. So E1 entrywise EK is a linear combination of EK minus 1, EK, and EK plus 1. And at least this coefficient and this coefficient is non-zero. We don't know about the AK star. We don't know if that's 0 or not. So we know those other two are non-zero. So here's a fundamental lemma in Suzuki's paper called the diamonds lemma. The next slide makes a lot more sense than this slide. Okay, but this is the precise statement. The next slide is the picture. I want you to remember the picture, not the precise statement. I have in, let me put this down. I have in L star says if I have three zeros in a row, then I must get a 0 here and a 0 here. It says if I have 3 zeros in a row, or column, because these things, the zero non-zero pattern is symmetric. 3 zeros in a row, then the things above and below must be 0. And now if I have 10 zeros in a row, then I have a whole pyramid of zeros on top, a whole pyramid of zeros on the bottom. It's very simple. For each L, now I'm going to take the things in the eigenspaces are actually going to be the first column of each E, right? So I'm going to take a specific vertex, project it into all the different eigenspaces. Okay, so the hypothesis here is that Ui entrywise Uj is orthogonal to eigenspaces k minus 1, k, and k plus 1, because that's exactly what we're assuming. Ij, k minus 1, k, and k plus 1 are all 0. So Ui entrywise Uj is orthogonal to U1 entrywise Uk. That's what we had. Now, swap things around. When we have that inner product, we can move the vectors any way we want. So put the j over here, put the k over there. That's exactly the same as what we had. So that's 0. And that's exactly the two entries, because we know that these coefficients, these prime parameters are non-zero. So therefore, must be orthogonal. That vector must be orthogonal to uk minus 1 and uk plus 1. Okay, so that's the proof. This is not the proof that you see in Suzuki's paper, but this is my proof. Okay, so that's the diamonds lemma. So that says, if you look in LJ star, you see any little cluster of zeros, then you can build those up to these diamonds of zeros, right? And I had an animation for you. I said, oh, well, let's take a 71 class association scheme with 2 Q-polynomial orderings. Just the diamonds lemma tells you so much already, but I don't have time to play that game right now. Suppose I did have a second Q-polynomial ordering. So suppose I have some large association scheme. I look at L5 star in this case, or LH star. Let me choose H equal 5. I know that the prime parameter 1, 4, 5 is non-zero. So I put a black box if I know it's non-zero. I know that 1, 3, 5 is 0 because 1 plus 3 is less than 5. So those are all forced to be zeros. The things here, here, and here are forced to be non-zero. Everything else in between, we don't know whether it's 0 or non-zero. Right? Now assume there's a second Q-polynomial ordering. So there's some simultaneous permutation of rows and columns that turns this into an irreducible tridiagonal matrix. Well, look at column 1. Eigenspace 1 is already attached to eigenspaces 4 and 6. The only other prime parameter that could be non-zero is 1, 1, and that's already forced to be 0. So this must be a 0. Look at eigenspace 4. It's already attached to 1 and 9. Therefore, all of these must be 0 except possibly the diagonal, right? The AI star. So you get a whole bunch of zeros because you know that there's at most 3 non-zeros in any column. And if there are 3, one of them has to be on the diagonal. So now you get a whole bunch of zeros. And let's call them prime parameters. The prime parameters in this permuted prime array, CL hat, AL hat, and BL hat. Now, the diamond lemma tells me that these 4 zeros force a little bit of zeros over here and here, but it doesn't give me everything I want. What do I have to work with? Are there any diagonal entries equal to 0? This lemma tells us as long as it's not the last one, or the last one in the Q-polynomial ordering, sorry, or the first one, then an AL hat that's equal to 0 forces A1 hat equal to 0. Can eigenspace E1 in the original ordering be the last one in the new Q-polynomial ordering? Well, it's already attached to 4 and 6. It's already got two neighbors in the representation diagram. So it can't be the tail of the path. So therefore, this is one of those things that the proper hypothesis for Dickie's lemma. So therefore, this diagonal entry is 0. And now look at what the diamonds do, right? Now it just topples and everything becomes 0. All of a sudden, you've got a very restricted situation. And you're going to be able to kill this off and show that this can't possibly be a Q-polynomial ordering, but we want to do things a little more carefully. So the next tool, which I'm going to prove with scaffolds tomorrow, is the boxed-in lemma. And again, I want you to believe the picture on the next slide and not the precise statement. Okay? The boxed-in lemma says if I have a non-zero prime parameter, and among the 9 things around it in this array, if I have inside LR star, if I have something non-zero, that is a black box, and among the 8 things around it, I have 4 zeros, then some two entries of the Krein array are equal. Some two entries of the Krein array are equal. Okay, so let me do the pictorial version of this. Okay, so if I have a non-zero prime parameter, the things above, think above as back, so that's a C, and the things to the right, that's forward, that's a B. CT star, T is the row, is equal to BS star. Have the things to the left is back, and when we go in our QIJK matrices, and the things below is forward. Row T, column S, then CS star is equal to BT star. If I have 4 zeros around a non-zero, where this is above and this is back, then those two C stars must be equal. And if it's down and forward, if those 4 things are all 0, then I have these 2 things are equal. So it's really, really nice, because remember what that thing looked like. There are all sorts of non-zeros surrounded by, they're boxed in by zeros, right? Oh, we're going to get this thing. We're going to look at this. Okay, we're going to. So now, suppose you have second Q-polynomial ordering, right? Take that starting point right there, and know that that thing is non-zero, and it's boxed in on the left and bottom, and that forces B1 star to be equal to CH minus 1 star. And remember, we're going to very quickly, from Dickie's lemma, we're going to have A1 star equal to 0. You know what's going to happen. And so B1 star is dimension minus 1, right? And that's a very strong restriction already. Now, what if you look instead of this one just above here, what if you look at the one just below? That's boxed in to the left and above. So that forces CH plus 1 star equal to C1 star, and that's 1. So things are very, very restricted. I think I'm going too fast. Questions? Here's the theorem that we're trying to prove. So Suzuki, and with this help from Mon to eliminate one struggling case, said if I have a Q-polynomial ordering 0, 1, 2, 3, and so on, and there's a second Q-polynomial ordering, and I'm not on a polygon where things are weird, then either the second Q-polynomial ordering is 0, 2, 4, 6, etc., and ends at 1, or it starts at D, goes to 1, goes back up to D, down to 2, and so on. Or it starts at D, goes down to 2, and so on. Or it goes up to D minus 1 and down to 2. In fact, once you know the first thing there, the others are kind of forced. Let's go back to the diagram and see why those other things all sort of come for free. So suppose you had a Q-polynomial ordering that started with 5, right? Well, you know 1 is already adjacent to 4 and 6, so it's not at the end. But you know that 5 is already adjacent to 10, right? And this, I'm just writing down a little graph, a path. I want a path where I is adjacent to j if I is not equal to j, but the Krein parameter Q1ij is non-zero. So 5 is already adjacent to 10, and 10 is already adjacent to 15, and 15 it gets a little bit. It gets bogged down when you get out towards the end, right? But you know that 1 is adjacent to 4, and 4 is adjacent to 9, and 9 is adjacent to 14. So you can decide a whole bunch of these things. And when I was preparing this, I thought, well, we should sit down and put together these little fragments of paths and figure out that there's basically a unique way to glue them all together to get a path for the whole thing. There really aren't that many possibilities. Once you start gluing all those together, you just have to figure out how to tie the laces at the end. Okay, so if this was 2, then you would know if this was in the second position, you would know that 1 is adjacent to 3, and 3 is adjacent to 5, and so on, and 2 is adjacent to 4, and 4 is adjacent to 6. So that's not too surprising that you would get this. As soon as you know that it started with 2, you sort of know what has to happen after that. Then the class number is very small. It's not so easy because it's too much at the end, too many laces to tie. So that's where things get hard, and I'm going to ignore that case where the class number is small. So that's the multiple polynomial orderings theorem, which is a very important paper for me, 1998, that Suzuki taught me a lot. Suzuki also proved that if you have an association scheme, which is Q-polynomial and imprimitive, then you have what Paul calls degenerate idempotents. You have EJs with repeated columns. And the ones with repeated columns have to either be 0, 2, 4, 6, etc., or just 0 and D. Those are the only degenerate idempotents. Other than a polygon, that's another problem. This is exactly the same as all of the AI stars equal to 0. That's Q-bipartite. Not because it looks anything like bipartite graphs, but parameter-wise, it's the dual of bipartite. I'd like to call it projective or something because they're actually lines through the origin. The Q-bipartite case means that the columns of E1 are closed in the multiplication by -1. So you have a polytope that's got north-south pole pairs. That's what Q-bipartite means. It should be projective or something else, because those are lines through the origin. Q-antipodal is not like antipodal. Instead of having all these antipodal fibers far apart, you've got what we had with the mutually unbiased bases and linked systems of symmetric designs. You got these big chunks, and between them are these sort of bipartite graphs, and the quotient scheme is complete. Okay, the subschemes are interesting. The quotient scheme is complete. In the p-antipodal world, the subschemes on the antipodal fibers are complete graphs, and the quotient scheme is interesting. But here in the Q-antipodal world, the sub-objects are interesting, and the quotient scheme is complete. Let's write those down in a different way. So one possibility is that the rank of E1 is 2, and we have a polygon. Let's pretend we understand polygons. The other possibility is that it's Q-bipartite, so the degenerate idempotents are 0, 2, 4, and 6, if and only if all the Qijks are 0 when I plus j plus k is odd. And Q-antipodal, now there's a really interesting thing in the Q-antipodal case, the Pijks are often 0. Q-antipodal, if I look at the LD star matrix, LD star has this backwards lambda property. It's M sub D like this, and then it changes to 1s and M sub D minus 1. So this backwards lambda property is what you see. That's what I'm trying to say here. Okay, and that's exactly for p-antipodal association schemes, antipodal distance regular graphs. That's what you see for L sub D. The PIJDs have this property. Okay, so those are the two big Suzuki theorems, and they both follow from this idea. They both follow, and I'm going to put the diagram on the board. I apologize for using board and slide at the same time. Oh, and wet markers, that thing is not going to help me. I want to think about what parameter did I use? I used H. So suppose I have LH star. I used boxes there, right? So that's non-zero, non-zero. Suppose I have these 4 entries equal to 0. That's the hypothesis. Suppose those 4 entries are 0, and I'm away from the boundary that H is not 1 or D. Let's see, H can't be 1. I guess if H is D, this is vacuous. I'm not sure why I allowed H equal D. And I'm assuming that the rank is at least 2 and D is at least 4. The possibility is H equal to D. This just cannot happen, right? So that's the claim. This cannot happen. And so how are we going to prove that? Well, we're going to use the boxed-in lemma. These two entries, just as we saw before, those two entries are boxed in, right? So by the boxed-in lemma, we look at article H, column 1, row H minus 1. That's this entry right here. It's boxed in, left and down tells me that B1 star is equal to, C1 star, so column 1 is equal to BH minus 1 star. Is that right? No, I think I said it backwards. Apologize. This should be correct. And now if I look at this entry instead, this is boxed in over here and here, and I get a C equal to another C. CH plus 1 star is equal to C1 star. And now we've used the fact that the S column of LR star is equal to the R column of LS star. And there's another application of this that I won't write down, is that CH minus 1 star is equal to CH plus 1 star. One of them is equal to B1, the other one is equal to C1 star. One is equal to B1 star, the other one is equal to C1 star. And C1 star is always 1 for any association scheme. Well, any Q-polynomial association scheme, you get a 1 here. And so B1 star and C1 star are 1, but we have this right here is an AI star, right? We're in this Q-polynomial ordering, and that is exactly AH star, and that's 0. And so if H is not equal to B, then that thing must be 0. And now you add up those three, and you get the dimension of the eigenspace is 2. And you're stuck with a polygon. So the whole thing follows from this, and I think, oops, that's where I'll stop for today. So thanks for your time.
Questions for Bill?
Yeah.
Is there a P-polynomial version of the diamond lemma? Dual result.
Should be true. Should be true. So we're saying that that if things A and B, the distance I, the distance J, and this distance cannot be equal to K minus 1, K, or K plus 1, then if I took something at distance K from this should not be equal to J minus 1, J, or J plus 1. Does anybody see why that? Right. Yeah. Yeah, I think that that's known. I'm embarrassed to say that I didn't check it, but I assumed that it was known in the P-polynomial world.
A question?
I think Paul's got a question.
Hold on a second. Okay.
Yeah.
Okay, so let's thank you again.
That's a lot.
And see you all in 2 hours, something.
Any soup dolphins?
What? Is
Late for
that-
lunch?
Yeah.
You're going for some shalom bottom.
Those are really good. They have another location. Sorry, I was hoping for a whole hour.
As many cookies.
The dumplings. Oh, okay. No, you're good. But we're okay.
You're happy.
The dumpling.
Yeah, you're happy.